All right, so in this video, we're going to go over an adiabatic flame uh, problem and try and find the temperature of this adiabatic flame Bunsen burner or whatnot. And for this question, we have these things for our natural gas. So it's 95% methane, 4% ethane, 1% propane. And that'll be our fuel component. And then the air is just going to be straight air from the atmosphere. So 79% nitrogen and then 21% oxygen. And we're going to consider this an ideal gas, and we have an excess of air at 20%. And there's a few assumptions with this problem. We're going to ignore the kinetic energy of any of the particles of air or fuel, and we're going to ignore the height difference that it goes through in the burner. And we're also considering this adiabatic, as I said before. So there's no heat loss at all through like the walls of the burner over here or through the tubing for the air or fuel. There's no heat loss at all. And so for the reactants, the enthalpies need to be the same for the reactants and then the products. So whatever goes in, so our air and our fuel are going to have a cumulative enthalpy. We'll just call it a cumulative enthalpy, and it needs to be the same of whatever comes out of this burner. So those enthalpies need to be the same, or the change in enthalpy has to be zero. Since our enthalpy going in is going to be the same as the enthalpy going out, we have this equation. If you remember, our change in enthalpy is equal to the internal energy plus PV, the PV work. And for this problem, we're going to set it up. I'm going to set it up like this just to explain it a little bit. It'll be so enthalpy in times some mass. Times some mass in is then going to equal our enthalpy out times some mass out. Right? So those two have to be equal. And, I can probably leave that. So let's set up a little a reaction for our burning of our fuel. So let's start with our methane. So CH4 plus O2 yields then our CO2 and water. Right? And to balance this equation, so we have 2 hydrogens and then 4 hydrogens over here. So we'll put a 2 in front of there. But then that gives us 4 oxygens on this side. So we need a 2 here. And that balances it out. So that'll be our reaction for just methane and then oxygen, the combustion reaction for methane and oxygen, giving us our products. But if you remember up here, we have our air is 79% N2 and 21% O2, right? So then we're going to have to add onto that with that oxygen is nitrogen, basically just along for the ride. So 79 over 21 N2. Sort of running out of room there. Oh well. So 79 over 21 N2, and then on the other side as well, so plus 79 over 21 N2. But since in this equation we are using 2 moles of O2, we would need to add in a 2 times the ratio of that nitrogen to oxygen in air, so plus 2 times our 79 over 21. That gives us the reaction for just methane. So then for our ethane, we'll have C2H6 plus O2 plus, let's just write it out, 79 over 21 N2 yields then again CO2 plus H2O plus then 79 over 21 and 2. And then to balance this equation out, we will have 7 over 2 here, and then 7 over 2 here, and then 3, 2, 2, 2, and then 3 oxygen, and then 7 over 2 here as well. Looks good. So these are just the two reaction equations for burning or combusting the two hydrocarbons in our natural gas. I'm not going to worry about propane for now, but I'll get to that later in once we get to the Python code. So when it comes to enthalpy, we can represent it like this. So we have our change in enthalpy, and then our change in enthalpy over temperature at constant pressure, plus then our change in enthalpy over change in pressure at constant temperature. And if you remember, for an ideal gas, this term goes to 0. So that one's just 0. We don't have to worry about it. And then this one we represent as CP, or specific heat. That's where we get our specific heat from. And you'll notice as temperatures increase higher and higher, our specific heat can change. So we'll need to change that as temperature increases as well. And we'll get to that once we get into the Python code. But just keep that in mind, that we will have to keep changing our specific heat as temperature changes as well. So it's not just going to be a constant. And then for our specific heat, so there's an equation in ChemCAD that I want to reference. So it's Y, let me pull it up. I think I have it somewhere. Yeah, here we go. So I'm going to copy it down. So Y equals A plus B times C over T, all that over hyperbolic sine of C over T squared, plus D times E over T cosine, or hyperbolic cosine of E over T, that squared as well. Okay, there we go. So this will give us our specific. So with this equation, what we're going to want to do is take the integral of our C over T times sine H, or we're going to take the integral of the entire equation, but just the parts that I'm going to worry about that are actually hard to take as an integral is the two fractions. And just by plugging them in to Wolfram alpha, you'll just get C times cotangent, or hyperbolic cotangent. So cotangent of C over T. So that's pretty easy. And then the integral of then our E over T, hyperbolic cosine of E over T, and T is temperature here, not time. Set that. And then after plugging this one into Wolfram alpha again, we get negative E hyperbolic tangent of H times E over T. There we go. So that's just the integrations of these two fractions right here. Doing that by hand is kind of pointless. And then, of course, just the integral of A would just be A times T. And then we'll multiply these by their coefficients, so D. Those will be negative like that. And we'll use this to put into Python here in a minute. Okay, so I think that is all of the equations I need to go over. I think we'll go ahead and jump over to Python real quick. Okay, so here all I have is just our document that we copied over from GitHub that had our CHE tools in it, and it's got our che.py or .py, and then our NumPy, SciPy, Optimize, and then just more tools from the CHE. And all I did here was just grab the properties for methane, ethane, propane, and oxygen, nitrogen, carbon dioxide, and water, just all of our components to the reaction that we're going to be doing. So what we want to do now is just define a function that's going to have our integrated terms from the CP equation that I was writing earlier. So we're just going to define this function as we'll just do int CP and then t, and our only return, and then what we want to return is just that equation. So it will be let's see, c dot or p dot cpiga, yeah. And we're just trying to grab our CHE tools from the document that I imported earlier. So we'll multiply this by t, because this is just our a term in that equation after it's been integrated, so we have to multiply by t. And then what we'll do is add, and then, p dot our b term times then the c term, there it is, times np dot, do they have hyperbolic cotangent? No, just regular. So it'll be times 1 over tangent h of p dot, then c term time, or divided by t this time. That's okay. So that is our entire second term, and then the third term. So we'll subtract d. I do that every time. P dot d times then e and tangent, hyperbolic tangent of h of then p dot ge divided by t. There we go. Looks all good. The next function that we want to define is one for the left-hand side with the zero part. The left-hand side of the equation equals 0, but it's the differences in the enthalpies. And we want to find those enthalpies at given temperatures. So we'll just define H and then just T. So then enthalpy at a given temperature, and what we want to return is just our what we're starting at. So the heats of formation. So P dot H of formation of ideal gas, and then plus our then function that we defined up here, so our equation, at whatever temperature our flame is at, minus whatever it was at room temperature, so 298 Kelvin. And then there's one thing that we need to do to this equation to keep units in check pretty much, and that is divide it by 1,000, and I'll show you here in a second. So if we do just p dot h, sorry, these are in let me see if I can just pull it up. That's not what I want. Yeah, so if we pull up methane, our heat of formation is in kmol, and then this is in just mole, joules per mole. So we need to divide this by 1,000 to get it into units that we can use and that match up nicely. That's all I wanted to do with that. Okay. If you think back to the problem that we're working with here is that we're not just burning methane or we're not just burning ethane. We have natural gas, which is methane, ethane, and propane. So we can't just say that there's one carbon atom and four hydrogen atoms on the reactant side of the equation, because there's not. We have methane, which is one carbon. We have ethane, which is two carbons, and then we also have propane, which is three carbons, and then the amount of hydrogens respectively. So we need to take that into consideration. So what we'll do is we'll do N fuel equals then NP array, and then what we have is it was point. Oh, let's see. Let me pull it up. 0.95. Then 0.4 and then 0.1. So that's methane, ethane, and propane. So then we need another array with the amount of carbons and hydrogens. So we'll do, let's see, fuel. Wow, I can't type today. Fuel CH. I think, yeah, that works. And we'll do another array and numpy array. But then this time it'll be, so methane is one carbon, four hydrogens, and ethane is two carbons, six hydrogens. Well, let me put this in brackets. And then, I did not. Propane is three carbons, eight hydrogens. So there we go. Now all we want to do is a matrix multiplication, but first we want to unpack it into the carbon and hydrogen atoms, or the numbers. So, and then we'll do N fuel times then fuel CH. Enter. So then let's see what NC is. 1.06 NH. Cool. It makes sense because since it's not just methane, we have 4% ethane and 1% 1% propane. We're going to have just a little bit more than one carbon atom on that side of the equation. Not much though, because it's still 95% methane. And then again, same story for hydrogen. I'm going to use the two balanced equations here to demonstrate this next point. So since we have, we know the amount of C atoms, right? And in this equation, we have one C on this side, and then CO2 on this side is 1. And then we have two carbons on this side, and then CO2 has a 2 in front. So that one is pretty straightforward. So it'll just, so CO2 is just NC. For our next one, where did it go? There we go. For the next one, our water, so we have 2 H2O, and let's see, we have 2 O2. And what you see here on the bottom one, we have 3 H2O and then 7 over 2 O2. So that is going to be, so N, let's put N. Now for the water, so H2O, we'll take a look at our reactions again. So we have the number of the waters here. So we have 2 waters and then 4 hydrogens on this side. We have 3 waters and 6 hydrogens. So that's pretty obvious that we just take the number of hydrogens and divide by 2. So we'll just do NH divided by 2. Now for our oxygen, what you'll see is we have one CO2 molecule plus then half of our O2 molecule of our H2O. So 1 plus half of 2 is 2 again, so then we have 2 O2. Then we have 2 plus then 3 divided by 2 is 1 half, so that's 3 and a half. 7 divided by 2 is 3 and a half. So that equals N CO2 plus then NH2O divided by 2. For our nitrogens, it's just going to be our 79 over 21 times the O2. Because this ratio stays the same. The nitrogen's just along for the ride. And if you remember in the problem statement, we have 20% excess of air. So what we can do is just take, we'll just call it excess air, and then that equals 1.2. So just 20% of whatever our oxygen is. So then times excess air. That looks good. Okay. So, and then we're going to make another array. We're going to add on to the N fuel, so then our NO2 NO2. Next is nitrogen, so N2, then CO2, and CO2, and then H2O. There we go. And then for our out, oh, I'm glad I caught that. Okay, so we don't, since these are in, we want to make sure that these are 0, because those exist only on the product side. So H2O and our carbon dioxide will be 0 going in, and then vice versa for the other side, our fuel going out would be 0 because we burnt all the fuel and used all that up, but then our reactants will have actual numbers in those spots. So we'll have zeros for our hydrocarbons in natural gas, and then for our I'll just, for now, let's do this. So then it'll be NCO2 and N2. So those, not N2, and H2O. Sorry, I got ahead of myself there. So that's just going to be our water and CO2. But now we have, since we have excess air, we're going to have air coming out with it, with our products. And we can specify this as, we'll do NO2 times excess air. Oh, you know what? Since I made this, let's make this 0.2, and then we'll add 1 onto that. Because now when I multiply by just 0.2, that gives us exactly how much excess there is. So that makes sense. Okay. Now that'll work out now. And then we have just our nitrogen along for the ride. Okay, there we go. Now we're ready to use our root function to find the temperature. So let's define another function. We'll call it temp, and then put in our vector, and then t equals, and our guess is just the first element, and our return is gonna be the dot product of our enthalpy of n out minus our then our enthalpy at room temperature, and then n in. Okay, there's that. So now we're ready to use our root function. So root temp, and then we'll just give it a guess. So 2000 kelvins. Let's see what we're getting. There we go. So 2063 kelvins, a very pretty hot flame is what we got. That is it. All right, so we took our percentages of methane, ethane, and propane, and then with our air, and calculated what our temperature would be if we burned our natural gas in an adiabatic situation with no heat losses. So this will be our temperature. That'll be it for this video. Thanks for watching.